This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. We have the pro version with the unlimited testing center and the free version without the unlimited testing center. We have interactive flashcards. We have full online lessons with videos and practice tests at the end. We also have unlimited practice testing on every topic that you can imagine for exam prep. This program comes with 100% full support from us here at electricalexamcoach.com. We just want to see you win. Let's get to it. Hey y'all, what's up? It's the Electrical Code Coach, and I'm super excited to offer this resource to you guys. It's 25 questions with full audio explanations. Before we get started, if you guys could do me a huge personal favor and hit that subscribe button and hit the notification bell button, that way we can spread the word and help more people. With that being said, I want to talk about the best way to use this resource. So each question, I'm going to speak it audibly and it'll list the answers below. But right after I'm done speaking it, go ahead and hit the pause button on the video and try to work through it on your own, and then you can hit the play button and see how I fully explain it and lead to the answer. I am the Electrical Code Coach, and if there's any way that I can help you in life or business, you can just email me at electricalcodecoach@gmail.com. Let's get to it. All right, guys, so I'm really excited to get started. We're going to be starting in dryers and building from there. What is the total demand for 11 dryers with a nameplate rating of 5,200 watts each using the standard method? Remember, when we're using the standard method, we're going to calculate dryers at a minimum of 5,000 VA or the nameplate rating, whichever is greater. So we take our 11 dryers, we multiply it by 5,200. That's going to give us 57,200. Now we're going to head over to table 220.54 and we're going to find out what the demand factor is for 11 dryers. We find out that the demand factor is 47%, so we take 57,200, multiply it by 0.47, that's going to give us 26,884, and we are going to select C. Great job. Let's get to it. What is the total demand for 3 ranges with a nameplate rating of 9,000 watts each using the standard method? Table 220.55, since our range falls in between 8 3/4 and 12, we're going to use column C for that number of ranges. We have 3 ranges, so we just head straight to column C. We're going to start on the far left hand of the table, find our 3 ranges, slide over to column C for 3 ranges, and we're going to select B. What size main overcurrent protection would you select with a total calculated load of 85,250 VAs on a 120/208 volt 3-phase system? So we're going to take and divide our total VA by the system voltage. With 3-phase, we're going to do a little bit of pre-work. First, we're going to take our 208 and multiply it by the square root of 3. That's going to give us a new value. Then we take our total VAs divided by this new value, and that's going to give us approximately 236 amps. In this case, we're 0.49 or greater, so we're going to round up to 237 amps. And we're going to head to table 240.6a. We're going to choose our next standard size, and we're going to select B. What is the allowable ampacity of a number 4 THHN copper conductor that's installed in a pipe with 9 current carrying conductors? When we're doing temperature corrections and bundling adjustments, we're going to start in the 90° C column of our ampacity table. We're going to find that number 4 in the 90° C column is good for 95 amps. Now we head to table 310.15 B3A in the 2017 and table 310.15 C1 in the 2020. We find our adjustment factor for 9 current carrying conductors, and it's 70%. Now we take our original ampacity multiplied by 0.70, and that's going to give us a new allowable ampacity of 66.5 amps. And we select B. What is the allowable ampacity of a 2-watt XHHW copper conductor that's installed in an area with an ambient temperature of 111 degrees Fahrenheit? When we're doing our temperature correction and bundling adjustments, we're going to start in the 90° C column. We're going to find that 2-watt copper in the 90° C column is good for 195 amps. Now we're going to head to our respective tables. We're going to find our temperature correction factor for 111 degrees Fahrenheit, being sure to start on the Fahrenheit side and then selecting from the 90° C column. We find that it's 87%, or 0.87. Now we take our original ampacity, we multiply it by 0.87, and that's going to give us a new allowable ampacity of 169.65 amps. And we select D. What is the allowable ampacity of a number 6 THHN aluminum conductor installed in a pipe with 11 current carrying conductors in an area with an ambient temperature of 32 degrees C? Starting in the 90 degrees C column, we'll find our original ampacity. We find out that number 6 in the aluminum column for 90 degrees C is going to be 55 amps. Now let's do our bundling adjustment. We're going to find that for 11 conductors, it's 50% or 0.50. Now we're going to head and do our temperature corrections. We find out that for 32 degrees C, it's 96% or 0.96. Now we take and bear the math out. We take 55 amps multiplied by 0.50 multiplied by 0.96, and that's going to give us a new allowable ampacity of 26.4. And we select B. Great job. What is the total calculated load after demand factors for a dwelling unit that has 4,500 square foot of main living space with the following appliances? An 1,100 watt dishwasher, a 13 kW range, a 5,200 watt dryer, and a 3,500 watt water heater. So we're going to take 4,500, multiply it by 3, which is our VAs per square foot, and that is going to give us 13,500. Then we're going to take and add to that our 2 small appliance and 1 laundry circuit at 4,500 VAs. We're going to take and add that all together, and then we're going to start a larger math problem over here to the side. Now we're going to take all of our appliances and total them together. So we take 1,100 plus 13,000 plus 5,200 plus 3,500, and that's going to give us a total of 22,800. We're going to take and add that to the side. Now we need to add those two together. That's going to give us 40,800. Now we're going to head to 220.82 and we're going to apply our demand factors. So we're going to take the first 10,000 at 100% and then do the remainder at 40%. So we take that 40,800, we're going to burn 10,000 and set it to the side, and we're going to be left with 30,800. Now we're going to take that 30,800, we're going to multiply it by 0.40, and that's going to give us 12,320. And we are going to take our original 10,000, we're going to add back our reduced load, and that's going to give us a total of 22,320. And we are going to select D. Great job. What is the total HVAC demand you would calculate for a dwelling unit with an AC compressor that's rated at 22 amps, using a 2.2 amp blower motor, and 3 baseboard heating units rated at 3,500 watts each on a 122/40 volt system using the optional method? So we go ahead and work out the AC, and now let's calculate the heating. So we take 3, which is the number of baseboard heaters, and we're going to multiply it by the wattage. That's going to give us 10,500 VAs. Now what we're going to do is we're going to be allowed to add a 65% demand factor to that, and that's going to reduce the load down to 6,825 VAs. And you still see that even with this reduced load and such a small number of baseboard heaters, that the heat still ends up being the larger load. So we're going to select the larger, and we are going to select B. What size copper conductors would you select for a 7.5 horsepower, 208 volt, 3-phase motor that has an FLA nameplate rating of 28.6 amps terminating to 60 degrees C terminals? So we're going to go through our initial steps here. Then we're going to head to table 430.250 because we're dealing with 3-phase. And we're going to go down on the left-hand side and find our horsepower. We're going to come over and tee off with our voltage, and we're going to find our motor's FLC. And in this case, it's going to be 24.2 amps. Now we have to take that 24.2 amps and we're going to multiply it by 1.25. That is going to give us a new amp draw of 30.25 amps. Now we're going to head to our primary ampacity table. And this is where we have to be careful. Our question states that we're terminating to 60 degree C terminals. So we have to be sure to head to the 60 degree C column. So we're on the left hand side. We go down in our 60 degree column until we find a wire that is going to cover our amp draw. And in this case, we find in the 60 degree C column that it's a 10 gauge wire. Great job. Let's get to it. What size short circuit ground fault protection would you select for a 5 horsepower, 208 volt AC 3-phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 26 amps using an inverse time breaker? We never size normal short circuit ground fault protection from the nameplate or FLA rating. It's just like normal circuit conductors. You're going to size it from the motor FLC. If the FLC is printed on the nameplate, we can use that. First thing we're going to do is go figure out what our FLC is. We know how to do this. Pause the video now, see if you can find out the motor FLC. So we use our FLC motor tab. That takes us to table 430.248. We're doing three-phase, so we need to flip over to 430.250. We're going to look down and find a 5 horsepower motor. Then we're going to slide over to our respective voltage. And in this case, it's going to be a 16.7 amp motor. What size short circuit ground fault protection would you select for a 7.5 horsepower, 460 volt AC 3-phase motor terminating 60 degree C terminals with a nameplate FLA rating of 9.9 amps using a non-time delay fuse? Remember, we're going to use our FLC and not our nameplate FLA rating. We're going to head to table 430.250 because it's 3-phase. We're going to find our FLC is 11 amps. Now we're going to head to table 430.250 and being very careful to select the correct device. In this case, it's a non-time delay fuse. And we find our multiplier is 300%. Now we're going to take 11 multiplied by 3, and that is going to give us 33. Now we're going to head to table 240.6a, and we're going to choose the next size up. And in this case, it's D. Great job. What size overload protection would you select for a 3 horsepower, 230 volt AC single phase motor terminating to 75 degree C terminals with a nameplate current rating of 15 amps? So we're going to follow these codes here, remembering the service factor and the temperature rise. For this motor, there's nothing listed, so it's going to fall under all other motors. We're going to take our nameplate FLA. We're going to multiply it by 1.15, and that's going to give us a new amp draw of 17.25. They don't make a 17.25 amp breaker. So we're going to head to table 240.6a, and for motor overload protection, we're always going to select the next size down, and we're going to select B. Great work. What size 4 square box would you select for 8 number 8 conductors? So let's all look at the table. As we jump in, this question is letting us know that it's a 4 square box. So we're going to be in the second part of that table from left to right. Those are just the simple square boxes. The ones below that are 4 and 11/16. So it's going to be one of those 3 answers that are in the 4 by section. Okay, so we know that we have number 8 conductors. So we're going to go over to our number 8 column, and we're going to start going down. First, we make sure we get in the right sub-column in the 4 square boxes, and then we're going to start there at the top. The first one is 6. Okay, that's not going to hold. The second one is 7. That's not going to hold. And it looks like it's going to be the third one, because anything past 7 is going to be required to be a larger box. So it'd be 8 and up. So in this case, we are going to use the third box, and we slide over and find out that it's a 4 by 2 1/8 4 square box. And we're going to select A. What is the total cubic inch volume for 3 10-gauge conductors and 5 8-gauge conductors? So we're going to head to our table 314.16b. We're going to find our 10-gauge conductor first. So we take it and we tee off, and we find that it's 2.50 for each one. So we take our 3 conductors, multiply it by 2.50, and that's going to give us 7.5. So now we go and we find our 8-gauge conductor, and we find out that it's 3.0. So we take our 5 conductors, multiply it by 3.0, and that's going to give us 15 cubic inches. Now we take and we add the 2 together, and that's going to give us 22.5 cubic inches. And we're going to select B. What is the total cubic inch volume you would have for a box that contained 3 number 12 hot conductors, 3 number 12 neutral conductors, 3 number 14 hot conductors, 3 number 14 neutral conductors, and 6 equipment grounding conductors in the 2017? So we're going to be referencing table 314.16b. And let's go ahead and count our 12s up. We have 3 hots, 3 neutrals, and because this is the largest conductor in the box, this is where we're going to account for our equipment grounds. It counts as 1, no matter how many there are, based off the largest conductor in the box. It's going to make our total 7. We know that our cubic inch volume for a number 12 is 2.25. We're going to take 7 multiplied by 2.25, and that's going to give us 15.75. Now let's account for the 14s. We have 3 hots, 3 neutrals, and we have nothing else because we've already accounted for the equipment grounds. That's going to total 6. Now our table lets us know that a 14 is good for 2.0. We're going to take our 6 conductors, multiply it by 2.0. That's going to give us 12. We're going to take our 12 that we have now. We're going to add in our original 15.75. That's going to give us 27.75. And we're going to select D. Great job. What is the total cubic inch volume you would calculate for a box that contains 8 12-gauge conductors and 2 single pole switches in a 2-gang box? All right, so first we're going to figure out what our cubic inch volume is for each conductor. Each one is 2.25. Now we need to take and total all this up. So right off the jump, we know that we have 8 12-gauge conductors. So we can go ahead and write down 8. Now we need to calculate how many we need to add to it based off the devices. Well, we have 2 single pole switches in a 2-gang box. So that's telling us that we have 2 device yokes. So what we're going to do in this case is we're going to add 2 for each one, which is going to be a total of 4. So we have 4 more conductors. In this case, all of our conductors are of the same size, so we're going to add it to the 12-gauge column. So each one, and we're going to take 8, our original base. We found out that we have 4 more that we have to add because of our devices. That's going to give us a total of 12. Now we take and multiply that by 2.25, and it's going to give us 27. And we select B. Great work. Let's try a different one. How many more 2-aught THHN conductors can you fit inside a piece of 3-inch Schedule 80 PVC that already contains 5 2-aught THHN conductors? So when we're dealing with conductors that are all of the same size and insulation rating, we're heading over to Annex C. When we get to Annex C, we're going to find our type of pipe, and we're going to make sure that we get the correct page number, being mindful of the at-risk symbols, not to get the compact conductor table. When we get there, we're going to find our insulation type on the left. We're going to come over to the next column and find our wire size, and then we're going to come off and tee off with the top and find our pipe size. So in this case, we're going to find that the total number it can fit is 11. So we're going to find out the total that we can have. We already have 5. We're wondering how many more we can fit in there. So if we take, and then we're just going to subtract it out to find out how many more we can fit. So we take our 11 that we can fit. We're going to subtract our 5 that we already have, and that's going to leave us with 6 that we can add. And we're going to select C. So if you came up to a pipe that had 5 2-aught THHN conductors in it, and you wanted to know how many more you could fit, you would go to this table, you would subtract your 5, and find out that you could legally fit 6 more in there. Now, getting them in there is, in the real world, it may be a different issue, but this would be what the code says you can take, and this is what your test would want to see if you got this question. Let's get to it. How many more 2-aught THHN conductors can you fit inside of a piece of 3-inch Schedule 80 PVC if it already contains 5 1-aught THHN conductors? Now there's a lot going on here, and there's a lot of math. So just take your time and do it one step at a time. You can do this. All right, so first we're going to find our type pipe in Table 4 because we want to figure out the total area that we're allowed to fill first. So we're going to look through here. We're going to find our type pipe. We're dealing with rigid PVC Schedule 80. All right, so when we find it, we're going to find our type of pipe. So we're going to use a straight edge. On the left-hand side, we're going to find 3-inch. Then we have more than 2 conductors, so we're going to use the 40% column. And we're going to find out that our 3-inch is good for 2.577 inches squared. 2.577 inches squared. Now, what we need to do is find our known conductor. So, in this case, we're going to be using Table 5, and we're going to go look for our known conductors. We know that we have 5 1-aught THHN conductors. So we're going to flip over a couple pages until we find THHN. Then we're going to use our straight edge until we find 1-aught. Then we need to make sure we come over to the inches squared column, and we're going to find out that our 1-aught THHN takes up approximately 0.1855 square inches. Each one of those conductors takes up that much space. Well, our question states that we have 5 of those conductors. So we take our value, Get my pointer out here. This is our base conductor. That's what 1 is. We have 5 of them, so we take our base and we're going to multiply it by the number of conductors that we have. And that's going to give us 0.9275. Okay, now we need to figure out how much space we have left to fill. So we're going to take our original total from here. We found out that we're allowed to fill up this much right here. We're going to take that original total and we are going to minus what we already have. We already have 5 1/0. So we're going to take our total minus the 5, and this is going to leave us an area that we're allowed to fill still. Now we're wanting to see in this area that's left over how many 2/0 we can fit. So what we have to do now is find out what the area of our 2/0 conductor is. So we head back to our table 5, chapter 9, table 5 table, slide down until we find 2/0. And when we tee off with inches squared in area, we're going to find that it's 0.2223. Each one of these takes up 0.2223. Now to figure out how many we can fit in that pipe, we're going to take our leftover total of what we had left to fill, and we're going to divide it by each one of these 2/0 conductors, so 0.2223. When we divide that, we're going to see that it goes into it 7.4 times. Now, we can't have 0.4 of a conductor, so on all of these problems, we have to round down, okay? There's no such thing as 0.4 of a conductor. So we can fit 7 more 2/0 THHN conductors inside of a piece of 3-inch Schedule 80 PVC if it already contains 5 1/0 THHN conductors. Great job. What is the available fill area in inches squared of a 2-inch, 18-inch long EMT nipple? So we're going to be dealing with Chapter 9, Table 4. Anytime we have anything to do with pipe fill, we're either going to be dealing with Annex C, Chapter 9, Table 4, or Chapter 9, Table 5. When we're just wanting pipe information, we're going to be dealing with Chapter 9, Table 4. So we head over to Chapter 9, Table 4 using our tab, and we're going to look at the black bold headings until we find the pipe EMT. When we find EMT, we're going to be looking across the top. The first column that we come to in the second subset of black headings is over 2 wires 40%. And then if you go over one column, it says 60%. And you may wonder why that's there. And that is there for your nipple fill. That lets you know what your available inches squared is when you're dealing with a nipple 24 inches or less. So when we're dealing with a nipple 24 inches or less, we're going to find our type pipe in Chapter 9, Table 4. And what we're going to do is we're going to come down and we're going to tee off with our type of pipe. In this case, it's 2-inch. So we use our straight edge to come down to 2-inch for our trade size. Then we're going to come over and we're going to find that our available fill area is 2.013 square inches. So that's how much we're allowed to fill it. So you're not allowed to fill a nipple up to 100%. You're only allowed to fill it up to 60%. And this is how you find how much available area you have. Now let's find how many conductors we can put in it. What size copper grounding electrode conductor would you select for a 400 amp service with 400 kc mil main copper service conductors? First thing we're going to establish is, does it mention the type of electrode? No, it does not, so we're going to use table 250.66 at face value. If we've tabbed our code book, we can use our GEC tab to head to table 250.66. If not, head to one of these 2 pages. When we get there, we read the black bold heading, we make sure we're in the right table, working our table from top to bottom and left to right, using the black bold headings to navigate. Starting on the left-hand side, let's be diligent to go back and look at our question. We're dealing with copper and copper, so we just have to take our time. Starting on the left-hand side, we're going to find our size conductors. We go down through, and our conductor falls in the over 350 through 600 kc mil, okay? So then we have to be careful to slide over to the copper GEC part of the table, and we're going to select a 1/0. Let's get to it. What size copper grounding electrode conductor would you select for a 400 amp service with parallel 2/0 copper main service conductors? All right, so this is where we've got to watch out. So when we go to table 250.66, it tells us to size our grounding electrode conductor based off the size of the hot conductors. But if you look right there, it says size of largest ungrounded conductors or equivalent area for parallel conductors. Okay, so this is table 250.66. In the second set of black bold headings on the left-hand side, it tells us to do it based off the largest ungrounded conductors or the parallel equivalent area. And we're going to learn about that now, so let's go ahead and get to it. First thing we're going to do, does it mention the type of electrode? The answer is no. So we're going to use table 250.66 at face value. If we have our codebook tab, we're going to use our GEC tab. If not, we're going to head to the correct page. Now the table says to size the wire based off the parallel equivalent area. So how many of you guys remember, we're in the Master Series, how many of you guys remember where to find the area of a conductor? Remember, we need it for voltage drop. What table is that? What table do we head to? We're going to head to Chapter 9, Table 8. Pause the video and we'll head there now. Okay, so when we get to Chapter 9, Table 8, we need to find our conductor. Remember, this table, you read it again from left to right, or top to bottom and left to right, using the black bold headings to navigate it. So first, remember, we had to always find our size conductor. So we come down to 2-aught. And then we're going to go jump over 2 little columns over to the circular mills in area. And that is going to be the area of our individual conductor, okay? So we're going to find the approximate area of the 2-aught conductor, and we find out that it's 133,100 per 2-aught conductor. That would be 133,100, okay? And we're dealing in KC mills now, but we're trying to figure out, okay? We're dealing in C mills now. If you cut it down, it would be KC mills, okay? We're dealing in C mills now, okay? And we're wanting to find out the parallel equivalent. So if we have 2 conductors in this parallel set, what we're going to do is just take those C mills and multiply it by 2. That's going to give us 266,200, okay? And that would be our C mills. Now what we do is we go back to table 250.66, and we're just going to find out where this parallel set falls. So when we get back to table 250.66, now we just need to take our total C mills and we need to find out where it falls in the column, okay? So starting on the left-hand side where copper is, because we're dealing with copper conductors, and we have to be careful here. Let's look at our question, copper, copper, so we're dealing with the 2 copper columns. So we go over here first and we size our ungrounded hot conductors using that new value as the approximate area, okay? So we come down and we're going to fall in the column that is over 3-aught but not larger than 350. Remember, that's in KC mills. So ours is 266,200, okay? So we're going to fall right there in that column. We're going to go over and we're going to find out that we're not required to use larger than a number 2. Next week, we're going to do a few more of these questions. They're kind of tricky if you don't watch it, but let's just recap very quickly. First thing that we have to do is figure out what conductor we're using. We're using a 2-aught conductor. Then we head to Chapter 9, Table 8, and find out the individual area for one of those conductors. Okay, our individual area was this right here, 133,100. Then we have 2 of them because we paralleled, so we're going to multiply that by 2. That's going to give us this new value in circular mills. So now we head back to table 250.66 and just find out where that fits. Remember, it says the size of the conductor or the area's equivalent. So if you were to take those 2 conductors together and make it one, this would end up the 266,200 would end up being the equivalent area. If you took there and measured it, that would be the equivalent area. You come back to the table and you just size it accordingly. Wherever it falls, whatever range it falls in on the copper side or aluminum, if you're doing aluminum, that's going to be whatever one you're going to use, and then you go over and select your GEC. Let's get to it. How many THHN number 12 conductors can you fit inside of a 2-inch, 22-inch long EMT nipple? Now, the key word that you want to watch out for here is nipple in your question, okay? Typically, they're always going to put the word nipple when you're testing. But if they happen to say a 24 or less inch piece of conduit, they technically don't have to say the word nipple, but most of the time they're going to. So just watch out. When you see the word nipple, think 60%. So when we look at this, we're going to go down, we're going to head to Chapter 9, Table 4. We're going to head over and we're going to find our type pipe. So in this case, we're using EMT again. So when we find EMT, we're going to head down to our table. In this case, we're using a piece of 2-inch EMT. So since it's a nipple, we're going to go to the 60% fill column. When we get there, we're first going to find our total area available to fill. In this case, it's 60%, which is 2.013. So now we know the total space that we're allowed to fill. Now we need to head over to table 5. Flip over a page or two, okay? And you're going to find THHN, okay? And you're going to find the approximate area of one number 12 THHN conductor. So when we find THHN in Chapter 9, Table 5, we're going to line up with the 12-gauge conductor. When we find the 12-gauge conductor, we're going to go over to the inches squared column. When we find the approximate inches squared, we're going to write that down. It's 0.0133. So a 12 is 0.0133 per conductor. We're trying to see how many we can fit inside of this nipple. Okay, so we take our overall available area, which was 2.013, and we're going to divide that by the individual conductor that we're trying to fit in there. So when we divide that out, that's going to give us 151.3 conductors. Now you can't have 0.3 of a conductor, so in pipe fill you always have to round down. There's no such thing as 0.3 conductors, and you can't fit any more than that, okay? So we have to work in whole conductors. So when we're dealing with pipe fill, we always round back down, and we have 151 conductors, and we're going to select B. That's 1,000,000 conductors, so you know, it feels like you could fill it up to 100%, but if you laid 151 of those conductors in there, it's going to take up approximately 60% of that pipe. Now, managing all that is a whole nother deal, okay? But we're just talking about the code. We're talking about how to find the available fill area. So anytime you're dealing with a nipple, you're out in the field, let's say you're going in between two panels or you're doing a generator, if you do a short nipple, 24 inches or less, you can fill that thing up to 60%. How you figure out how many you can fit is you will go to your Chapter 9 Table 4 table, figure out the value for 60%, then head over to Chapter 9 Table 5, figure out your individual conductor, and then just divide it out, and that'll tell you how many of those conductors that you can fit in there. How many more, number 8, THWN-2 conductors can you fit inside of a piece of 1-inch, Schedule 80, PVC if it already contains 3, number 12, THWN-2 conductors? First, we're going to find our pipe type in Table 4. Always find your pipe type first. So we're going to find, in this case, we're looking for Schedule 80 PVC. So when we head to Chapter 9, Table 4, we're going to find Schedule 80 PVC. And when we get there, we're going to be looking in over 2 wires. So we first read our black bold heading, Schedule 80 PVC. Now we come to the second subset of black bold headings, and we're going to find the over 2 wires column. That's because this pipe now contains over 2 wires. We're allowed to fill any pipe that contains over 2 wires up to 40% of that pipe. So we're going to find our size. So we take a straight edge. We're going to go down and find our trade size of 1 inch, and we are going to find that at 1 inch, you can fill it to 0.275. Okay, so write that down. Now we're going to go find our individual conductors. First, find the conductors that you already know. In this case, it says the pipe already contains 3 number 12s. So go find those first. So you head to Chapter 9, Table 5. You find your individual conductor. So we're dealing with THWN-2. And when we get to THWN-2, we're going to find that it's 0.0133. That's for the individual number 12 conductor. Now we have 3 of those in our pipe, so we need to multiply that by 3. So when we multiply that by 3, it's going to give us 0.0399. And now what we do is we take our original available fill and we minus what we already have. So our original available fill for the 1 inch Schedule 80 was 0.275. Then we minus the 0.0399, and that's going to give us the available area that is left to fill. Okay, we need to first figure out what is the available area left to fill. So it's 0.2351. Now what we're going to do is we're going to find out the volume, okay, the area in inches squared for a number 8, the individual number 8. So we head back to our column. It happens to be THWN-2 as well. We're going to slide down to a number 8, making sure that we're in the inches squared column, and it's going to be 0.0366. That's the individual one. We're trying to figure out how many more we can fit in there. So we're going to take our area that's left available to fill. We had 0.2351 left to fill. We're going to divide that by the individual number 8 conductor, and it's going to let us know how many that we can put in there. In this case, it's 6.4. Well, we can't have 0.4 of a conductor, so we're going to round down to 6. So these are things that you just have to practice. You go through it over and over, and you can take, unlimited practice tests on the Electrical Exam Coach website. Awesome. Let's get to it. How many number 6 RHH conductors can you fit inside of a piece of 1.5-inch RMC? When we're dealing with conductors that are all of the same size and insulation, we can use NEC. It starts on page 712 in the 2017 and on page 729 in the 2020. So when we get there, we see a list of a lot of different types of pipes. So what we're going to do is we're going to find our type of pipe. And when we find our type of pipe, we're going to use a piece of paper as a straight edge to make sure that we get the correct page number. Remembering not to use the type of pipe that has the A and the at risk, because that is for compact conductors only. Only use that if your question specifies compact conductors. So you're always going to want to use the first one that comes in line. So let's use the first RMC. And whatever page number it says for you, whatever code book you're in, go ahead and flip there now. Now once we get there, we need to find our type of insulation, our wire size, and our pipe size. So we're going to use a piece of paper as a straight edge or a pencil, and we're going to come down and we're going to find RHH as our insulation type. Then we're going to find our number 6 conductor, and we're going to come down and we're going to tee off with the type pipe that we have. We have 1.5 inches. So when we find that we get a number 6 in 1.5 inches in RHH, we find that we can fit 8 conductors in there. Great job. How many more number 10 THWN-2 conductors can you fit inside a piece of 3/4 inch Schedule 80 PVC that already contains 3 number 12 THWN-2 conductors? Now we're going to go through this step by step. So the first thing we're going to do is find our pipe type in Table 4. So when you find our pipe type and we get to that section, now we need to find the approximate area that we're allowed to fill. We're going to find the approximate area based off the number of conductors. We're going to use the 40% column because we have more than 2 conductors. We're going to find that we have in 3/4 inch Schedule 80, we have 0.164 inches cubed that we can fill. Now we need to find our first conductor. We know that we have 3 number 12s inside of that pipe. So we're going to flip over to Chapter 9, Table 5, and we are going to find a 12-gauge conductor, and we're going to use a straight edge, and we're going to find out that each 12-gauge conductor, it takes up 0.0133. Now we need to take that 0.0133 and multiply it by 3 because our question stated that we already have 3 number 12s in the pipe. That is going to give us, when we bear that math out, it's 0.0399. Now we need to figure out how many number 10s we can fit in there with this scenario. So what we're going to do is we're going to take our original total. This was our original total that we are allowed to fill. We're going to minus what we already have, which is the 0.0399. That's going to give us 0.1241 that we're allowed to fill still. We're still allowed to fill this much. Now we want to figure out how many number 10s we can fit in there. So let's go figure out the area of a number 10. When we do that and we look at our table, we tee off, we find out that 0.0211 is what each conductor is going to take up for a number 10. So what we do now is we take our remainder after our 12s were installed, and we have this much left to fill. We're going to divide that by what a single number 10 is. That's going to tell us that we can fit 5.88 more number 10s inside that pipe. Well, there's no such thing as 0.88 of a conductor, so we're going to round down, and that is going to give us D, 5. We can fit 5 more number 10 THWN-2 conductors inside a piece of 3/4 inch Schedule 80 PVC if it already contains 3 number 12s. Let's get to it. This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. We have the Pro version with the Unlimited Testing Center and the free version without the Unlimited Testing Center. We have interactive flashcards. We have full online lessons with videos and practice tests at the end. We also have unlimited practice testing on every topic that you can imagine for exam prep. This program comes with 100% full support from us here at electricalexamcoach.com. We just want to see you win. Let's get to it.